Hello everyone, and welcome to Building Rapid CVE Responses into Cloud Foundry for Kubernetes. My name is Dave Walter, and I've been an engineer on the CF for K8s team since its inception in 2019.
My name is Andrew Wittrock, and I am the Project Management Committee Lead overseeing Cloud Foundry for Kubernetes.
Today, we are going to talk about the challenges operators face in trying to keep a production CF for K8s foundation and the applications running on it secure and safe. Unfortunately, the programs that are the building blocks of modern internet-connected platforms are exposed to a near constant threat of attack from vulnerabilities in software and malicious users looking to exploit them. This is such a large problem that the MITRE Corporation maintains and publishes a formal common vulnerability and exposure list to track new vulnerabilities as they are discovered and reported. When a CVE is reported, platform operators want a way to patch their deployments quickly and easily with as little risk as possible. By far the most common areas of concern are the base operating system for the platform's infrastructure and the common libraries and utilities that are installed. With traditional Cloud Foundry running on top of BOSH, these are distributed in two ways. The first is a stem cell image that forms the basis for the individual VM instances that make up the platform. The stem cell is an infrastructure-specific disk image that is combined with packages from BOSH releases to form the file system for VMs created by BOSH during the deployment. The second is the stack that is used in combination with artifacts from the application staging process to form the file system for running application containers. Both are examples of just-in-time image creation, which makes responding to CVEs fairly straightforward. The platform can be redeployed with a new stem cell or stack release without upgrading any of the other component versions. This greatly reduces the surface area of the change, which in turn reduces the risk involved in the upgrade. The updated stem cell tells BOSH to recreate all VMs in the platform using the new stem cell image. Meanwhile, the updated stack package on the Diego cells causes them to be updated. Part of this process involves relocating all application instances to other cells. When an application instance is moved to another cell, the stack on that cell is automatically incorporated into the new instance's file system. Eventually, all the cells will be updated with the new stack, and so the application instances will be updated. However, deploying on Kubernetes is very different to deploying on BOSH. To tell us more, here's Andrew.
So what is different in Kubernetes? In the Kubernetes world, all runtime is precompiled into Open Containers Initiative compliant images. There are no stem cells. Instead of the just-in-time compilation world of CF for VMs, the K8s world is more ahead-of-time compilation. The image reference is essentially just another field on your object. Since Kubernetes relies on operators to provide the chain of custody of an image, additional methods must be used to recompile your artifacts. This presents some challenges and suggests solutions. What does the image contain? How can I build an image once I know that? And what tools are available to help? How do I actually know what is in my image? I could run the image myself and poke around, but that may be of limited value. Simply looking at the image tells us relatively little about it. I can inspect the various layers in the image, but all source code information is lost unless explicitly included. Luckily, there are tools to help. Open Containers Initiative specification to the rescue. There are predefined annotations we can use. Among them are source and revision. Source points to the URL to find the source code, and revision will point to a git SHA or tag. We can embed this information into an image at build time, and later we can retrieve this information when an image needs to be rebuilt. The source code location and revision combined with build configuration allows image building as necessary. How do I build my images? There are various methods to build OCI images. We have many cloud-native buildpack-based images. These are built with CNB compatible tooling like Pack or KPack, which implement the CNB lifecycle. These tools allow us to leverage teams dedicated to ensuring base images are kept up to date. And it provides a common way to build images, reducing uncertainty and complexity. We also have Dockerfile-based images. These are built with tools like Docker or Builda. While CNBs are extremely helpful, sometimes we need a different abstraction for more bespoke artifacts. Regardless of the tool set, we have a set of base images that we use to reduce surface area. We might use Scratch, or use one of the Paketo buildpacks base images, or Ubuntu base images. In order to build images, we need to acquire the source code for runtime applications. The toolset we currently use in CF for K8s is the Carvel toolchain. We use YTT for template processing and CAP for deploying Cloud Foundry. Carvel also provides a few more tools that we can use. In this case, we're pulling two other tools out of the toolbox called Vendor and kbld. Vendor is used to fetch application source code that is not represented in the same repository as the release templates. Here, we have a vendor configuration for fetching Cloud Controller source code. We configure where the source code should go, what to clone, and specify the URL and revision. Kbld is the abstraction over build commands. Kbld allows us to use a common format to delegate to multiple different build systems. In our case, Docker builds and Pack CNB builds. Kbld becomes the build interface without worrying about tool specifics at build time. This simplifies the process and provides better visibility into the build time instructions, embedding them in configuration rather than build time command line magic. Here, we have a sample kbld configuration for a pack-based image flow. This configuration is for the Cloud Controller, which was sourced with Vendor. Since we're using multiple tools from the same tool chain, the path field parallels the path in the Vendor configuration. A builder and build packs are provided, just as one would when building with the Pack CLI. The OCI image metadata is appended via the image labels build pack by providing appropriate environment variables. Here is a configuration for a Dockerfile-based image. The path to the Dockerfile is provided, along with some configuration. Since most of the build information is contained within the Dockerfile, the additional fields boil down to Docker command line options. The source code labels are appended with standard Docker label options. We provide a thin processing script to provide values to the build templates to render kbld configuration. This shell script calls another script to generate values as inputs to our YTT templates. This will render the kbld configuration files with proper values and run the kbld configuration against YAML that references the images. This produces an output lock file, which can be parsed to update references or be consumed by operators. An operator can utilize the configuration to implement their own update loop, whether that be manual or automation. And now I'll pass it back to Dave. He'll talk about detecting CVEs in images and how one might implement a full loop in automation.
Thanks. As Andrew mentioned, the challenge now is how to detect CVEs in the system images included in CF for K8s and how to react when one is found. It is worth pointing out that the remainder of the concepts that I'm about to present are still theoretical and have not yet been implemented. Here, we need to split the system images into two distinct sets, those that we can rebuild and those we cannot. The system images that, for a variety of reasons, we cannot rebuild include the Kpack images and the builder image that includes the stack and the build packs, as well as more standalone components such as Istio, Minio, and Postgres. For these, we need to rely on consuming new releases of the corresponding components and releasing new versions as necessary. For the images that can be rebuilt, a simplistic approach is to rebuild every image when a CVE is detected in any of them. A list of images to check can be generated using kbld from the Carvel set of tools. kbld's primary purpose is to orchestrate image building, but it can also automatically find image references within a set of templates and produce an image lock file. Once a complete list of images included in CF for K8s is generated, it can be filtered to remove those that cannot be rebuilt. Once there's a list of images, we can use a tool called Trivy to scan for high and critical CVEs. Trivy is a simple and comprehensive vulnerability scanner for container images and file systems. As I mentioned earlier, if a CVE is found in any rebuildable image, this could trigger a rebuild of all images, regardless of whether a particular image is affected by a CVE or not. With the work we've already done to standardize the component image build process, rebuilding the images is actually the easy part. The OCI labels on each image can be used to clone each source repository at the appropriate commit SHA. This ensures that the exact same source code is used to build the new image. The image build script for that component can then be run to rebuild all the images it includes. The last step is to aggregate all the kbld image lock files that the build scripts generate into a single directory that can be used by operators to update their foundations with the new images. The challenge here is to ensure that images for new versions of a component are not overridden by rebuilt images for an older version. For this reason, our initial thought is to attach a tarball of the directory of lock files as a GitHub release artifact, rather than committing it to the repository. Of course, all of this will be automated in CI, with the ultimate goal of automatically producing new patch releases whenever a set of images is produced in response to a CVE being detected. What about the application containers, I hear you ask? Happily, they are already protected. When the Kpack builder image that includes the stack is updated, Kpack automatically recreates all application workload images. The new image controller component of the CF API watches for these new images, finds the stateful sets for the corresponding workloads, and updates the image reference, which causes them to be recreated by Kubernetes.
So far, we've covered the following. CVEs are an ever-looming threat. CF for VMs uses an approach that works in its own ecosystem, while CF for K8s must use a different remediation strategy. Component images are divided into images that rely on upstream bumps and platform components that are rebuilt for CF for K8s. Application workload images are rebuilt by Kpack tooling updates. We've also learned some of the toolset we can employ to build component images. We can apply source code information to our images as OCI labels to provide insight into the package. Using vendor, we can clone any needed source code. kbld allows us to interact with multiple build tools, committing build configuration rather than relying on environment variables and command line magic. Once we can build images, we can set out to detect CVEs with Trivy. With the ability to build images and detect CVEs, we can automate the process to produce new kbld lock files. Employing this strategy will allow operators to patch component images on their existing platform. With these tools, you can keep your Cloud Foundry for Kubernetes cluster up to date and remediate any CVEs that pop up. From Dave and myself, thank you for attending the session, and we hope you'll join us for the following Q&A session.
Sweet. I see we had the same wardrobe choice this morning.
Of course. So, see if there's any questions to pop up as people filter in. But if there's anything you missed during the presentation, you can add it now.
Yeah, one thing I did want to mention was the second half of the talk about how we would then go on to automate this to produce patch releases. It's definitely like an MVP simplistic approach. There are more sophisticated approaches such as pack rebase for the images that are produced with pack, and more sophisticated methods of detecting CVEs in specific images and only rebuilding those. But that would be, I think, more engineering effort to get that into a production-ready implementation. So this was our thoughts for, like I say, an MVP that would allow us to respond to CVEs as they are detected in the software.
Any question from Bronson over here, which is how often do you scan for CVEs? May have missed it. We didn't actually mention it there. We're still sort of going through the paces of setting up our CI for it right now. So optimally, it would be a pretty regular approach. So at least sort of daily to check the images because it's a pretty low cost operation. But if you were going to implement this yourself, if you just wanted to, however you want, I would recommend, like I said, at least daily. Hopefully that sort of answers.
Yeah, I'm not sure what the cadence is for updating the Trivy database of CVEs to know what would make sense there, because there's no point scanning more frequently than that.
Yep. Yeah, I guess that's one point I don't know, but yeah, that makes sense. Ideally, all the tools will be provided so we can cut patch releases, and anyone could also rely on the tooling to build their own images so that you wouldn't need to wait for that to be published.
That's the nice thing about generating kbld lock files. They can be layered in as YTT overlays by the operator rather than it being included in the release. So yeah, it's definitely something that can be run by anybody. That's our goal, is to try and package this process into the component repositories and into CF4Case itself so that it is runnable by anybody.